So this is the example 2 for our tutorial. Estimate the maximum boundary layer thickness and the drag force due to friction on the side of a ship that measure 40 meter long with a submerged depth of 8 meter. Assuming the side of the ship is approximated as a flat plate, the ship travel at 10 meter per second. Use the empirical methods and compare with the result using the power law model. Okay, so here again, you need to read the question and then I hope you could imagine uh, the situation. So it is about a ship here. So, and then this is a ship, for example. So, and then it is made 40 meters long. It's quite straightforward here. And then I hope you could understand the meaning of the depth of 8 meter. So mean the depth of 8 meter is, so the submerged area is 8 meter. Okay, why? Because in this situation, you have two type of fluid. One is air and one is water. So normally at this situation, we will focus on water because water has higher, 10 times higher, not 10 times, 1,000 times, I think. 1,000 times, different value of viscosity. Okay, so in terms of density and viscosity, so it's totally different. So means that because water has very high density and also the viscosity, so means that the resistance will comes from water. Might be so. The resistance comes from air, it exists, but it may be too small relative to the what we get from water. It for means that in this situation we could neglect the resistance that comes from air. Okay, so and then if the length, okay, ship is curved. Okay, the design of ship may be something curved like this, but to simplify the calculation as stated here, so we just imagine that this is actually a flat plate. Okay, so and then means that now we have a long flat plate like this. The length here is 40 meter long and the width here is 8 meter. Okay, so and then I hope you could imagine that if you see experimental work of boundary layer, so you could do a few orientation to represent the condition of boundary layer. For example, if you have water flow from left to right like this, so it means that you have a few orientation. You may put your flat plate vertical like this. You may also put your plate horizontal like this, or maybe you could put your plate, okay, in certain angle. It's okay because it will create totally the same behavior of boundary layer. Okay, that's why in this situation you will find that this plate is actually vertical. So is that okay? Yes, it's actually okay. It is totally similar if you put a plate of 40 times 8 meter horizontal like this one. Instead of we put a vertical like this one, it is okay to put a vertical, a horizontal plate like this. Okay. So and then the ship is traveled at 10 meter per second. And then now in this question, we need to compare with the power law model. So again, so let's take property of water at 5 degrees Celsius. So means from that table, we will use a property of water at 5 degrees Celsius. So we could calculate the tau naught here by using this equation, and we will get 82.80 Pascal. So we could calculate the shear velocity. So the calculation is actually same with the previous tutorial. So we get 0.288 meter per second. And then we have this equation. We substitute the value, then we could get the delta is 0.384 meter. Okay, this is what we get from the numerical. From the empirical form, and then we calculate the drag force. We have the value of CD here. We substitute the value of Reynolds number, so we get the CD is 0.001904. And then we could calculate the drag force by using this equation. I think you know, this is the area of the plate, 40 times 8. And then this is the speed of the water. So this is the value. The drag force is 30,464 Newton. Okay, then this is the value that we get from the empirical form. Now, how to assume or how to solve this problem by using the power law? Okay, to solve this problem by using power law, we need to determine the velocity profile. So, how to determine the velocity profile? I think you remember when we learned about the power law, I give you the range here. So, let's say we check the Reynolds number. So, and then we found it is 2.6 times 10 to the power of 8. So, means that it is lay on this range. So, then we could assume that maybe the velocity profile can be written as u over u equal y over delta to the power of 1 over 9. Okay, because it's depend on the Reynolds numbers. So, and then what we need to do is, from this velocity profile, we do the, we start our calculation with von Karman, and then we equalize with Blasius calculation. So let's say from the Blasius calculation for n equal to 9 is given as this one. So this is the shear stress calculated by using the idea of Blasius. So, and then some textbook, they will give you nu over u delta. And some textbook, they will give you as mu over rho u delta. So please do not confuse yourself, because it is actually the same equation. So you need to remember the relationship between dynamic and kinematic viscosity can be written as mu rho nu. So you could know, you could change this equation into this. So this is not a different equation. It is actually the same equation. So what we do is, okay, I cut this one. Okay, so we start with the von Karman. We substitute the value of theta here, and you need to calculate the value of theta for this velocity profile. So if you do, you substitute in the equation, theta equal u over u 1 minus u over u dy, and the limit is from 0 to delta, and you will find it is equal to 9 over 110. So after that, okay, we make it faster. So we equalize these two shear stresses, means the value from the von Karman with the value of Blasius. And we could we could calculate the value of delta is 0.433x over Reynolds number to the power of 1 over 5. So, and then we substitute the value, means the value of Reynolds number here. Okay, we know that our plate is 40 meter long and 8 meter width. Okay, we substitute this number to get Reynolds number. We substitute the value of 40 in this x. So this x is length 40. So you will get the delta is 0.358 meters. So if we compare the delta from empirical method, it is 0.384, and delta from power law method, it is 0.358, or a little bit thinner. So means if we do the percentage, so we found that, okay, the result from power law method is lower. The difference is about 6.77%. So mean the percentage here is still less than 10%. So means that it maybe can be considered as a correct answer. Okay, so means that maybe the length and the speed is not too high and too long, so you will get a same almost considerable answer between empirical and power law. Both are, can be accepted, because it is just only 3 centimeters, 3 centimeters difference. Okay. However, if we calculate the drag force for according to the uh, power law form, okay, we could calculate the value of CD here. Okay, you know that we already could calculate the value of delta, and then you do the integration work again and again. Okay, you may see the previous notes, and then we could get the value of CD, and we use this value of CD. We substitute all the parameters here, and we could get it is 23,000 Newton. So then if we compare the value of drag force from the empirical method, it is 30,000 Newton. And the drag force from the power law method, it is 23,000 Newton. So if we calculate the percentage, we found it show a huge difference. So the difference is almost 22.8%. So means that maybe the thickness of boundary layer, it can be accepted. Okay, it's acceptable, it's still in acceptable range, the error or the percentage, but the drag force give us totally a big difference. So it is almost 1/4. Okay, quarter, the error is quarter, almost a quarter of them is not calculated. So means that here we could show that the empirical method is actually more accurate than the power law method, because normally if we compare with the experimental value, normally the value will be near to the empirical method. It is because, as I said previously, the empirical method, the equation that comes out from the empirical method is actually the curve fitting from the experimental works.